Now, I want to talk about the triple integrals. So let's start triple integrals. So if we have some region bounded by a surface, any kind of surface which is bounded by it. If I want to know what is the volume of this bounded region, bounded part of space, I want to find the volume, I should do almost the same thing as I did for area. I should take integral of 1 dx, dy, dz. Now we have 3 variables because it's volume, it's not area anymore, over this region. So if I show this region with R, I should take the integral over R. It means I should tell you what are the bounds for X, what are the bounds for Y, what are the bounds for Z. And actually it is pretty similar to the previous one. So let's start with more explicit examples. Let's compute just an example of triple integrals. Compute this triple integral, say e to the y, or maybe it would be hard, e to the x, y plus, let's just go with the example of the book, 2z. Integral, compute this integral, dz, dy, dx. The bounds for z are 0 to x plus y, the bounds for y are 0 to x, and the bounds for x are 0 to 2. Compute this integral. Okay, think about this one for a few minutes, and then I will solve it. Okay, whenever you have the final answer, you can write it in the chat, and then I would wait until one person solve it, and then I would write the solution. Might take 30 minutes. Oh, really? Don't think so. Okay, let's do it. Seems there is no answer. Or should I wait? Oh, can we divide it by 3 if we get no? That's not correct. Let's see, what is it really hard? We are computing the integral with respect to z. So we should start with, okay, I can give you more time. Yeah, sorry. That's a good idea. I can wait. Okay, now I know why it takes a lot of time. Okay, let's start. First, I should compute this integral. It's an integral in terms of z. Well, e to the x times y plus e to the x, 2e to the x z. Its integral with respect to z is equal to, I should just multiply it by z for the first part. And yes, you need integration by part at some point. That is true. Plus e to the x, z squared over 2. And the bounds for z are x plus y and 0, which means we are going to get e to the x, y times x plus y, plus e to the x times x plus y squared minus 0. Well, this is equal to, well, I could, yeah, that's correct. We could bring e to the x outside of the integral too. That is correct because it's constant with respect to z. So it is equal to x y e to the x plus y squared e to the x plus x squared e to the x plus y squared e to the x plus 2xy e to the x. Well, the sum is equal to x squared e to the x. Oh, it seems we have an answer. That's amazing. We will see that. Plus 2y squared e to the x plus 3xy e to the x. Okay, so that's the answer for the first integral. Now I should take integral of what I had with respect to y, which means integral of e to the x. I can factor e to the x, x squared plus 3xy plus 2y squared. I should compute this integral with respect to y. Well, as you mentioned earlier, e to the x comes out of the integral. It's constant. I'm taking integral with respect to y. X is like a constant. So I should take integral of x squared plus 3xy plus 2y squared dy. The first one would be x squared y plus 3 over 2xy squared plus 2 over 3y cubed. Y is supposed to change from x to 0. Well, I should just plug in y as x. What I would get here is e to the x, x cubed plus 3 over 2 x cubed plus 2 over 3 x cubed minus 0. If I let y to be 0, everything would be 0. Okay, what is this sum? This sum is x e to the x times x cubed times a constant number. What is that constant number? It's 6. 6 plus 9 plus 4. If I'm right, it's 19 over 6 e to the x, x cubed. Now, this is the last part, which apparently it's a little bit challenging. Now I should compute the integral with respect to x. From 0 to 2. Okay, so how can I do that? So 19 over 6 is a constant number. It comes out. I should compute the integral of e to the x, x cubed dx. How can I compute this integral? It's integration by parts. I need to do integration by parts. Okay. Oh, you change your answer or you simplified that? It seems you change your answer. Oh yeah. Okay. Now I need to do integration by part. Integration. What does integration? Maybe I should go to the second page. I want to compute the integral of x cubed e to the x dx. So I should decide about u and v. What is u here? What is v here? Okay. If you've reviewed your integration by parts, tabular integration is very easy here. Yeah, it might be, but let's stick to integration by. Let's do integration by parts. So what is u here? What is v here? The point is that there is a part which I want to take its derivative. I want to take derivative of x cubed, right? So remember, maybe I should just write a very short review here. Integration by parts says integral of duv is equal to uv minus integral of u dv. So that's what integration by parts means. Okay, so yeah, by tabular integration, it just means, you know, there's this table. I never did that, right? Derivative here, integral here. Sorry, I'm not really good at that. I should do this more kind of classical approach, just writing down line by line. But yeah, you can do it definitely if it helps you to keep track of what is what, and it makes it a little bit easier to simplify things. Yeah, that would help. Especially, I think it helps with x to the n e to the x. That is correct. So now I should decide what is du and what is b. What is du here? Well, du, I can take du to be e to the x dx, and I can take v to be x cubed. The integration by part tells me this integral would be equal to uv minus u dv. Okay, if du is e to the x dx, what is u? Well, u is just e to the x, because if I take derivative of this thing, I can see, well, derivative of e to the x with respect to x is itself, so du would be e to the x dx, right? So this, by integration by parts, this thing is equal to e to the x cubed minus integral of u dv. Now I should take derivative of x cubed, which is 3x squared dx. So there is another integration by parts. So e to the x cubed minus 3, another integral. This other integral is e to the x squared dx. Again, I should decide what is du and what is v. Just like the previous time, I take du to be e to the x dx, and v should be the remaining part. And again, like the previous case, if du is e to the x dx, u itself is e to the x. So this is going to be equal to uv, which is e to the x squared, minus integral of u dv, which is 2x dx. I can plug in this thing here. It would be e to the x squared minus 2, another integral. What is that other integral? It's integral of e to the x dx. Again, I should tell you what is du and what is v. Du is e to the x dx, v is x. Well, if du is that, u itself is e to the x, so integration by part tells me it is equal to e to the x minus integral of u dv. But here dv is just dx. And integral of e to the x dx is just e to the x. So I would get e to the x minus e to the x. So that's the final thing I would get. But remember, in the previous slide, we had 19/6 behind it. So we have x cubed e to the x minus 3 x squared e to the x minus 2x e to the x minus e to the x, 2 and 0. You should not compute it at 2 and compute it at 0 and subtract it. And I would trust you. Oh, okay. The book has an approximation. Well, let me look at your answer. I think they're the same, right? 19e squared. Yeah, that is correct. So the answer is equal to, apparently the answer is equal to 19e squared over 3 plus 1, which is approximately 66. So that would be the answer. Any question here? So maybe I should go back. Any question? Okay. If not, we can continue. So as you can see in this section, I really try to follow the examples of the book. The real reason is that these integrals can become pretty hard if you don't follow the very well-known examples, if you change just one number integral, there is no reason you can compute the integral anymore. It's unlike derivative. You can basically take derivative of anything. That's not the case about integral. If you just combine things, the integral might become very hard. So we see another example here. Actually, even the book has not done the integral completely. It just says the book is using integration tables. So there are some there's an appendix in the book, appendix B. There are integration tables there. Even in the question, which I want to tell you now, the book itself is using the integration table. So what is the question? The question is find the volume of the ellipsoid. So I wouldn't do this one completely because even as I told you, the book hasn't really done this integral. It's used, at some point it used the integration tables. It just says integral of something is equal to something else. So, but I would just tell you what should be the correct formulation. So we have an ellipsoid. If I divide everything by 16, I would get x squared over 4 plus y squared over 4 plus z squared over 16 equals 1. This is an equation of an ellipsoid like this. And we want to find the volume of this ellipsoid. Okay. The volume of a region of space bounded by a surface is equal to integral of 1 dx dy dz. We can do it in different directions. For this question, I mean, dx dy and dz, the order sometimes make it easier or harder. The order the book has chosen is dz dy dx, but it really doesn't matter. It doesn't matter at all, actually, for this example. It's completely, well, it's as symmetric as it should be here. It really doesn't matter in which order you write dx dy dz. Okay, now I should find the bounds for each of them. What are the bounds for z? I want to find the bounds for z. So the idea is to isolate z using this formula. Okay, so z is equal to 16 minus 4x squared minus 4y squared, square root of that. When I take the square root, I would get plus or minus, right? So these are the bounds for the function. Minus the square root of 16 minus 4x squared minus 4y squared to square root of 16 minus 4x squared minus 4y squared. What about, so these are the bounds for z. I wouldn't write it here. What about y? Well, simply just ignore z. And it is also interesting to think about it a little bit. That's also another interesting thing you can think about. Why this way of finding bounds really work? Why am I ignoring one variable? But anyway, if I ignore z, I want to find the bounds for y, I would just ignore z. I would get this equation. It means y squared is 16 minus 4x squared over 4. Therefore, y would be plus or minus the square root of 16 minus 4x squared over 4. These are the bounds for y. And if I even ignore y, I would get 4x squared equals 16, which means x squared equals to 4, or x is equal to plus or minus 2. These are the bounds for x. And if we compute this integral, we would get the volume of this region. I'm not going to do that. The integration is not really easy. It gets really messy very fast. There will be arc signs and radicals and multiplication of these things. So it's not a simple integral to do, but that's the vol. Now, if we could compute this integral, which we can with a little patience, that would be the volume of this region. Okay. Now now that we know how to compute these integrals, actually you can compute the volume of a sphere yourself. Maybe another good example is to compute the volume of a sphere and see, you would really get what you would expect. So you would have a proof for the volume of, so actually I ask you, what is the area of sphere and volume of sphere? One of them is 4/3πr². The other one is 4πr². Actually, if you have one, you can compute the other one. If you take derivative of this one, you can get the other one. If you take kind of integral of the other one, you can get this one. So if you have one of these things, it would be interesting for you to think about why there is this relation between these two things. If you take derivative of volume of the sphere, you get the surface area. If you take integral of the surface area, you get volume. But one thing you need to know is that if you want to prove these two formulas, you at least need to get one of them. And then, for example, at least you need to get volume. And then by taking derivative of the volume, you can get the surface area. So you should know, you should be able to prove at least one of these two formulas, and then using derivative of, or integral to get to the other one. So I guess you never knew the proof of why the volume of a sphere is this thing, 4/3πr². Now, using the integrals we just saw, the triple integral, you can really prove this thing. You can really compute the volume of a sphere, and you can really see what they told you is correct. That is really the volume of a sphere. So that's something you can do if you haven't done that before. Okay. Any question up to this point? No, there isn't any question? Okay. Okay, we get to the section 14.7. Triple integrals. In cylindrical and spherical coordinates. I like to do one example in each, although it's not really new. It's similar to the double integrals we did using polar coordinates. It's kind of similar. Remember that in three-dimensional space, we have rectangular coordinates, which we have x, y, and z. We have cylindrical coordinates, which are r, theta, and z. This is something we talked about. And the relationship between them is that x is equal to r cosine of theta, y is equal to r sine of theta, well, and z is equal to z, obviously. Now, this change of coordinates sometimes helps us to compute some integral. Okay, let's see one example. So suppose this is our question. Find, again, I would follow the example of the book. Find the volume of the region bounded by the sphere. Bounded the volume of the region bounded by the sphere x squared plus y squared plus z squared equals 4. And well, maybe I should write first. I mean, suppose you have a sphere like this. This is the sphere we have. And then we have a cylinder with equation r equals to sine of theta. Well, you should really sketch to see what is this cylinder, but it's actually a cylindrical surface. There is a cylindrical surface like this. This cylindrical surface would cut something out from this sphere. There would be a part of the sphere which this cylinder cuts. And the question is, what is the volume of that part which this cylinder cuts from this sphere? You can try to compute it. I can try to see if I can show this one to you using this application. So try to solve it. You need to use, you should use the cylindrical coordinates. That's the hints. Let's also see if we can, if I can show this thing to, if you can really see how it looks like. So we have two surfaces. One of them is sphere where z is equal to 4 minus x squared minus y squared, square root of that. That would be half of the circle. Maybe if I change the bounds, it would be work better, not sure, yeah. And then I have the minus that thing. So this is our sphere. Maybe I would reduce the transparency a little bit. So this is our sphere. We can see the sphere here. Now we have one more thing. We have a function r equals, r is equal to 2 sine of theta, 2 sine of, well, how can I write theta? Does it understand if I write theta? Oh yeah, it does. So, and z is, say, minus 10 and 10. So as you can see, this, well, this cylinder would cut something from this sphere, right? There is some region which is inside both of these two things. It's inside cylinder, and it's also inside the sphere. Now, what I'm interested in, maybe if I reduce these ranges, I can take a look inside that exactly. Inside this region, there is something down there. I want to know what is volume of that. And this is a pretty advanced thing. If we don't have these tools of derivative of integral and integral, it's pretty hard to compute. There is no way to compute these things. I mean, we are computing the volumes of intersection of surfaces, and these things are pretty hard. I mean, these tools which humans have generated through years in math and physics, integrals and derivative, it's pretty amazing. Okay, so try to do that. We want to compute this region. So does the question make sense to everyone now? There's a region cut out by this sphere with this, by the inside this sphere by this cylinder, and we want to find what is the volume of that. Think about it for a few minutes. I write the equations here for you again. X squared plus y squared plus z squared equals 4. That's our sphere. Y equals 2 sine theta is our cylinder. Why is this thing a cylinder though? Y equals 2 sine theta. Why is it a cylinder? That's one question you should ask yourself and answer. But anyway, even without answering that question, you should be able, even without imagining these things, that's the power of calculus. Even without seeing the pictures, you should be able to follow just the computations and get the correct answer. It is similar to what we did with polar coordinates. That is true. So the idea here is to use the cylindrical coordinates. So in cylindrical coordinates, x is equal to r cosine theta, and y is equal to r sine theta, right? So what is x squared? It's gonna be r squared cosine theta squared. What is y squared? It's r squared sine theta squared. This means this equation of this sphere here, we have x squared plus y squared plus z squared. In cylindrical coordinates, it would be x squared would be r squared cosine theta squared plus y squared would be r squared sine theta squared plus z squared equals 4. Here, if I factor r squared, I would get cosine theta squared plus sine of theta squared, which is 1. So r squared plus z squared equals 4. That's the equation of sphere in cylindrical coordinates. So if we want to use cylindrical coordinates, the idea is that we should first write down this equation in cylindrical coordinates. What about the second one? Y equals 2 sine theta. What would be the equation of this cylinder in y equals in cylindrical coordinates? Does anyone know? Well, y is equal to r sine of theta, which is supposed to be equal to 2 sine of theta, right? I just, instead of y, I just write r sine theta. So here, instead of y, I just write r sine of theta. So r sine of theta equals 2 sine of theta. It means r is equal to 2. If it's correct for any theta, it means r is equal to 2. Okay. That's the bound, right? This is the bound of the region, not the inside of the region. So here we should compute the integral of, we want to find the volume. We should compute the volume of the, oh yeah, that is true. Did I? Oh yeah, sorry, I made a small mistake. It's not y, it's r. Thank you for letting me know. So we don't need to do anything about it. We can just keep it like that. R is equal to sine of theta. That was the question, right? Yeah. So so volume is equal to 1 integral of 1 dx dy dz, but we can change that to cylindrical coordinates. If you remember, I told you dx and dy is equal to r dr d theta, and then we have dz there. right? So what are the bounds for, the order would matter for just sake of simplicity. Some order might be easier than the other one. Here, the order which the book has chosen, I would go with that one, is dz, dr, d theta. Okay, so I should first say what are the bounds for z. Okay, I know z squared plus r squared is equal to 4. I would isolate z. It would be 4 minus r squared, square root of that, plus or minus. So it's between minus 4 minus r squared up to 4 minus r squared. So this is the bound. These are the bounds for r, for z, I'm sorry. These are the bounds for z. What are the bounds for r? Well, let's take a look at these surfaces. So what are the values of r? If we look at the graph of these two surfaces carefully, this is the region we want to compute its volume, and this is the center. So here at this center, r is minimum. R is actually 0 there because we are on the origin. And at this point, it's maximized. It's because it's on the surface of the sphere, which is 2. So it seems r goes from 0 to 2. What about theta? How can we find the bounds for theta? Well, what is theta here? Look at this plane. Theta, what is theta here? Theta here is, can anyone tell me what is theta there? The angle. How does the angle change? So if this is our three-dimensional picture, this is our sphere, and then there is a cylinder we have, which looks like this. The cylinder looks like this. Maybe I should do it with another color. The cylinder is like this. Okay, if I look at this two-dimensional XY plane, this cross section, I have this circle. This circle is this one in XY plane. And then I have this blue circle. This blue circle is this one. I hope it makes sense. This is the red one is the cross section of the sphere. The blue one is the cross section of the cylinder. Okay. So what are the values of theta? The theta here starts at 0. It starts here. It starts at 0. It goes up to here, which is pi. So theta changes from 0 to pi. Does it make sense to everyone? If it's confusing, ask. So 0 to 2, 0 to pi. Does this, so this is the three-dimensional picture. This is the two-dimensional picture. It's kind of, the two-dimensional picture is like the floor in three-dimensional picture. It's the 0 level in three-dimensional picture. It's where z is 0. We have a red circle there. We have a blue circle inside it. If I look at just that two-dimensional plane at z equal to 0 inside the three-dimensional space, I have this red circle. I have a blue circle inside it. And theta goes, well, I mean, the region starts from here. And for example, for these points, it's 0. It goes up, gets to pi. So theta changes from 0 to pi. So I should compute this integral. Well, I mean, we can. The question is why we don't plug in r equals to sine theta, but we don't need to. you see, when we are taking integral in terms of ZR and theta, everything should be in terms of ZR and theta. And if it is in terms of R, Z, and theta, we don't need to change them. We can, but we don't need to. Also note that we already have chosen that equation, R equals 2 sine of theta, for understanding the bounds, right? We use that. Sorry, here I made a mistake. It's not 0 from 2, it's 2 sine of theta. Actually, there is a simple mistake here. The value of R equals 2 sine of theta. It's the maximum value of R. So R here at the center is 0. It would get to up to 2 sine theta. I think I wrote a very hard example maybe, especially because it's only the first day that you are seeing the integrals. It might be a little confusing and overwhelming. So let me review one more time maybe. So in order to compute the volume, I should take integral of 1 dx dy dz, right? But here it would be easier to do it using cylindrical coordinates. Now, cylindrical coordinates, the variables are r, theta, and z. So I should use dr, d theta, and dz. We saw in the previous example that dx dy are equal to r dr d theta. So instead of dx dy, I can just write r dr d theta, and there we have dz. So the only thing which remains is to find the bounds for z, r, and theta. In order to find the bounds for z, it's simple. We can just use the equation z squared plus r squared equals to 4. I can isolate z. Z would be equal to plus or minus the square root of 4 minus r squared. Z would go from one of them to the other one. That would be the bounds for z. The second step is to find the bounds for r. The bounds for r are a little bit more complicated. I can see the bounds for r using this picture I have there. If I look at the cross section with 0, there is this sphere, which its cross section looks like this circle, is this circle. And then I have a cylinder, which if I look at its cross section with 0 set, again, it would be another circle, right? R is the distance from the origin. In any direction, R would show me the distance of these points from the origin. It starts at 0, gets to this point on this blue region. As it said, R is 2 sine theta. So it starts at 0, goes up to 2 sine theta. So the region, the bounds for R are 0 and 2 sine theta. And finally, I need to say what are the sums for theta. I start from this direction, I go up, 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 and then there. Here is 0, here is pi. So theta goes from 0 to pi. If I write down these bounds, this would be the integral I would get. If I compute this integral, I would get the region of that area. Again, it's not an easy integral. It's not hard. There's some integration by parts and things like that. So I would leave it to you if you like it. You can take a look at the book to see how it's computed. You really don't have time today for the details of these integrals, but that's the way to do it. Now we can, so is there any question here? Does it make sense? Kind of makes sense because it's, I mean, I know it takes a lot of time to get used to these things. One bad thing about summer courses is that we have a lot of sessions just in one day, like 4 hours and 30 minutes in one day. It's so compact that you don't have time to digest these things. I've started from the basics of like in multiple integrals, and we got to quite advanced things. So I know it's not really easy to digest everything. Oh, okay, there's a question. Where did the 1 go in the last equation? 1, which one? This one? It's multiplied by r. Is that what you mean? Yeah, okay. Yeah. So, yep, you're welcome. So let's do one more example. Now, this time, let's do spherical coordinates. So again, I would follow an example of the book. Find the volume of the region bounded below by the cone, upper part of the cone, upper nape of the cone, z squared equals x squared plus y squared. This cone looks like this. This is a cone, and sphere x squared plus y squared plus z squared equals 9. And then we have this sphere, and I'm asking for this region which this cone cuts out of the sphere. What is the volume of that? Okay, think about this one for a few minutes too. So for the midterm, if you look at there is a feedback section. In the feedback, I wrote where you lost points. You can look at that so you see where you didn't get the points. And the reason I didn't write the answer to the midterm is that the midterm, the topics in the midterm, they wouldn't appear in the final. I thought you might not be really interested now to look at the answer, like the answers for the midterm, because if you want to focus on the final, but you can definitely ask me about things you didn't get perfect score and see why you didn't get. So again, this one should be integral of 1 dx dy dz. That should be the volume, but we should, if I show this region with R, it should be over this region R. And we should find what are the bounds for this region. So yeah, I would remind you. So for spherical coordinates, yeah. So the idea here is to use spherical coordinates. I would write them. So spherical coordinate system, we use rho, phi, and theta, and x is rho sine of phi, cosine of theta. Y is rho sine of phi, sine of theta, and z is rho cosine of phi. So you should use these equations to change them. So for example, what would be the equation of the sphere? So we had x squared plus y squared plus z squared equals 9. What would be the equation of the sphere using these equations? Well, x squared plus y squared plus z squared means the distance from the origin. That would be x squared plus y squared plus z squared. That is exactly rho. Rho is distance from the origin. So it means rho squared is 9, which means rho is 3. So one of the equations reduces to just rho equals to 3. If you are not sure about that, you can try it to see that. You can use these equations to compute x squared plus y squared plus z squared. You would see, if you do that, you would see sine squared plus cosine squared, these kind of things, they add up to get 1. So finally, you would get rho squared. So it means rho squared would be equal to 9, which means rho is 3. We are assuming rho is positive. Because it's distance, we are assuming it's positive. So it wouldn't be minus 3, it would be plus 3. Okay, I would write it. So I should compute the integral of 1 dx dy dz. It's a little challenging to do this thing. As I told you, for example, in cylindrical or in polar coordinates, dx dy dz was equal to r dr d theta dz. We can do the same thing here in spherical coordinates. We can compute what is dx dy dz. We can do that. It would be rho squared sine of phi d rho d phi d theta. So just like that, we can here, we have the formula for x, we have the formula for y, we have the formula for z. We should take d of all of them and wedge product them, which means just multiply them in some sense. And that's what we would get. So the integral of 1 would be integral of, well, 1 dx dy dz would be integral of rho squared sine of phi d rho d phi d theta. I should decide what are the bounds for rho, phi, and theta. The last one is theta, I'm sorry. This is theta. So what are the bounds for rho? Well, rho is between 0 to 3, right? I mean, at the center it's 0, at most it would be 3. It's a cone, intersection of a cone with a sphere, so rho would go from 0 to 3. What about phi? What are the bounds for phi? Well, if we look at the picture here, this is the sphere, this is the cone. I'm looking at this picture from one side, okay? Phi goes from here to here. Here, phi is actually pi over 4. Well, I should probably explain a little more. So if you remember in spherical coordinates, phi is the angle from the z direction to any point. So if I have any point here, P, phi would be this angle. Now, if I have this cone here inside this sphere, the angle goes from 0 here on the z direction itself, phi is 0. Phi becomes larger and larger and larger up to this cone itself. And on this cone, it's pi over 4. So phi goes from 0 to pi over 4. So it goes from 0 to pi over 4. What about theta? Theta is this angle. So if I have this cone, theta is this angle which goes around this cone. And actually, as you can see, it goes from 0, goes around once completely to 2 pi. So theta is between 0 and 2 pi. So if we come back here, theta goes from 0 to 2 pi. And this is the integral we should compute. Again, it's not an easy integral, and I wouldn't do that. I just want to give you an idea. And then if you compute this, you would get the volume of this part, which this cone cuts out of the sphere. Okay, the last section of this chapter is about Jacobian. I really don't want to talk about that. Because it takes a while to digest things I told you to get to a new part. I think, and it's not really necessary now for the scope of this course. So that's something interesting if you want to read. Also, well, as another topic you can teach for extra credit, you can think about Jacobian. Also about chapter 15, vector analysis. That's another thing you can teach and record yourself for extra credit. That's pretty amazing topic. On Tuesday, I would just solve examples and problems which you might see of that type in the exam. I wouldn't teach you anything new on Tuesday. And on Thursday, we would have exam. The exam would be pretty similar to the exam we had on midterm. You just attend through Zoom, and we would proctor you you should upload your exam to Blackboard, and everything would be similar. Is there any question?
I have a question.
Yes.
You might have already did this, but could you outline the textbook chapters which are going to be covered on the exam?
Yeah, I would do that again. So, as you know, we had 4 important chapters in the book. Chapters 11 and 12 were in the midterms. Chapter 13 and 14 would be in the exam, but because of this storm, I just taught you chapter 14 this week. So I told you that chapter 14 would appear only as bonus questions, only the things I told you today. And chapter 13 would appear completely on the exam. So what sections? So the sections which I would cover in the exam would be, in chapter 13, would be functions of several variables. Well, I mean, in some sense, it would be bonus, but it would be in the exam. So it really doesn't matter. If you solve it, you would get the grade. I mean, you don't need to think about it as a bonus question. You can solve the questions from today, the integrals, and you would get your grade. It would appear on final. But because it's very close to the exam, even if you don't solve these things, if you solve everything else completely, you can get the complete grade. Okay, functions of several variable, limits and continuity, partial derivatives, differential, chain rule, directional derivative, and gradient. These are from chapter 13. From chapter 14, we have things we talked today. Iterated integrals, area, double and triple integrals, volume, well, surface area, volume, cylindrical, and spherical coordinates. These are the things you should expect to see in the exam. Okay, any other question?
I have a question related. It's personal. It's related to the midterm. Should I wait?
Yeah. If you have a question about your midterm, yeah.
Oh, okay. It's just about where I lost points.
Yeah. So, yeah. Is there any other general questions about the course or about any explicit question about something I talked about? We can discuss now. If not.
I have a question about the integrals and the coordinate system. So
Yeah.
thing just like how we plug in and find the bounds for like if it's r theta or theta or raw like that. Like we don't actually have to solve the integral itself, right? Because it could get really complicated.
Well, I mean, well, it depends. I mean, I might ask you to solve it in the exam. But if I do, it wouldn't be a very hard integral. The integrals I wrote now, some of them, they can be quite complicated. Some of them are not really hard, it just takes time. And if you want to get to the final answer, you should solve it. So it really depends. I mean, it might be a hard integral and I might just ask you to write down to set up the integral, you know. Or it might be an integral which you can do it. It's not hard. I might ask you to compute this integral. It might not be a hard integral. So it really depends on the question. I can't tell from now.
Yeah, and also about the coordinate system, I know that we first learned them before the midterm.
Yeah.
The context of testing the coordinate system, would it be related back to what we learned before, like the context, or that just appears in the integral section?
Yeah, I mean, we learned it there because I don't remember why really it's written there in the book. I think the correct place for that is here, actually. And I had in mind to teach polar and cylindrical coordinates here. That was my original idea. But it's really good that I didn't do that, because all this fiasco and this storm and things like that, we wouldn't have enough time. So I remember at some point we had extra time and I taught you spherical and cylindrical coordinates back then. But really the place to use it is here.
Okay.
And yeah.
Okay, thank you.
Yeah, you're welcome. Okay, so I would stop recording the video. So this is the kind of end of this chapter. So goodbye, the people who watch from YouTube.